So Quicksort. So Quicksort is on average runs in O of log. Let's turn off the into shape. O of log n log n time. That's the runtime for Quicksort in general, as the average runtime. However, its worst case runtime is as follows, which is O of n squared. Now there's other sorting algorithms like merge sort or Tim sort that guarantee no matter that its worst case scenario is n log n, but they all come with disadvantages, like extra storage space usage and the like. Quicksort you can do in place. And we can, and as you watch the videos, you'll see there's ways to manipulate Quicksort so we don't get into this n log n situation. Okay, but Quicksort in general is a recursive sorting algorithm, and we're gonna kind of work on it by showing you what we can do with it. So the basic idea, the conceptual idea behind Quicksort is that given this array of numbers, all right.
Can you share your screen?
Oh yes, my bad, sorry. All right, the idea behind Quicksort is given an array of numbers over here, or a list of or an array list of numbers. Okay, we've got some item. We choose what's called a pivot. Now we typically choose the pivot like this, but we just simply choose the very first item as our pivot, just for simplicity's sake. Okay. And the idea behind Quicksort is that we've got X as our pivot. Okay. And then what we're going to do is that we're going to transform X. So we're going to transform the array into following. We're going to transform it into 3 sections. X, which is our pivot, everything that's less than X, and a pile of everything that's greater than X. The idea here is that we take everything and we just separate it out. Now this separating it out into these sections, of course, takes O of n time because every item is getting compared to one item, which is X. Okay, make sense? So we just simply say, hey, let's rearrange our array and turn it into this. It's very easy to do if you don't care about doing it in place, because you just simply say, hey, I'm going to make a linked list. Left list is everything less than X. Right list is everything greater than X. Okay, then what do? We do this recursively. We then do Quicksort on the left side and Quicksort on the right side. And then eventually what's going to happen is that we you know, and since that keeps recursing, it's eventually all going to be sorted. Okay, how long does it take? Well, if we're on average with the pivot's going to be somewhere on average, the pivot's going to be like a median item. Ideally, we'd want the median item. So let's say we get the median item. Okay, if we grab the median item for our pivot each time, and there's a bit of manipulation we can do to achieve this fact, then we can just simply shift. Then we can basically, well, we've just basically, when we do recursion, we do it on half of one side, half of the original, half of n, and on half of n. So 2 halves of n. So in other words, we've just taken this problem of sorting and we've reduced the search space by half. So we can keep reducing it into half. And what ends up happening, so, is basically if I take this array, right, and I split it in half, say I've got 8 items here. So this will be 4 items, split this into 4 items. Those 4s will be split into 2s. And the 2s will be split into 1s. Basically, I'll do 3 layer. I'm going to be doing 1 operation of Quicksort, 2 operations of Quicksort, 3 operations of Quicksort. In other words, I'll be doing log n operations of Quicksort, and each layer takes O of n time because each of those items are going to be compared once to one item. Make sense? So it ends up being n log n, which is kind of our theoretical minimum for sorting. And theoretical as in like math theorem kind of theoretical minimum. There are some tricks we can do if we know how many items we have and we've got parallel processing going on, but with one processor, this is our best bet. So how does this actually work? Well, to do it in place, what we do is that we're going to choose our pivot as the first item. So let's say we've got, and I'll choose some, I'm going to choose, let's see, 5, and then I'll do 1, 2, 3, 4, 5. Already did 5, 6, 7, 8. And I'll go ahead and do 9 over here. So here's how Quicksort works. All right, I've got this layer of Quicksort. What I'm going to do is, if I want to sort this using Quicksort, I'm going to choose 5 as our pivot. Okay, and then I create 2 variables. I create one called up at the beginning of the array, or up at the beginning of our section of the array, because this could just be a subsection of the array, right? If we're doing this recursively, this could be an array or it could be a subsection of the array. Regardless, for the portion we are sorting, at the beginning we create up, and at the end we create down. And what up does is that, as you can imagine, it goes up, it iterates up through this array, and down is going to iterate down through the array. But not like taking turns. What up is going to do is that it is going to look up for the first item bigger than the pivot. So up looks for the first item bigger than the pivot. So what we do is that up goes over here. Is 2 bigger? No. Up goes over here. Is 3 bigger? No. Up goes over here. Is 6 bigger than our pivot? Yes, it is. 6 is bigger than 5. I learned that in 3rd grade. I'm very proud of myself. Okay, so we look up for this item. So now that we found the first item that's bigger than our pivot, we now start with down. Down says, okay, is 7, down looks for the first item that is smaller than the pivot. So up looks for bigger, down looks for smaller. Nice and convenient like that. So down, is 7 smaller? No. Is 4 smaller? Yes. Okay. So now, and so up's found the first time bigger, down's found the first time smaller. Now what? You swap them. Not up and down. You swap what they were at. So 4 goes here, and 6 goes here. Okay, and now repeat. Just keep doing this. So up looks for the first item that is bigger, which will be 8. Down looks for the first item that's smaller, which is 1. Okay. And then, so we stop now and we swap them. And that was 1 and then 8. Okay. Up looks for the first item that is bigger. And down will look for the first item that's smaller. And here we actually end up at our end condition, which is that up and down have crossed. They have crossed the beams, which you are not supposed to do, except in this case, we do want to do that because that's our end condition. All right, I'm losing the track. Okay, so we have now since when they cross, and you've been following this algorithm, okay, you'll find that there have been that actually something interesting has happened. We've actually successfully subdivided this array. We subdivided it into something very close to what we want to do for our recursive step, or sorry, for our step, which is that we have our pivot x, we have everything less than x over here, and we have everything greater than x over here, which is pretty cool, right? It's like a magic trick, only it's boring. So now that we've done that, we basically do one last thing. We swap down with the pivot. So what we do is that we're going to swap whatever's at down with whatever's at our pivot value is. Very convenient that I end up at 1, 2, 3, 4, 5, completely intentional. Yes.
In that case, if we take the middle as the pivot, would that say that the runtime would be a tiny bit faster? than
No,
what-
because you have no way of guaranteeing that what's going to be in the middle is going to evenly divide it's going to be close to the median value.
But then we don't have to swap the middle.
You don't know but you don't know what the subdivision of the array is going to be. You don't know if it's going to evenly split. Like, as you'll see, we could choose a very bad pivot. Okay. I'm going to show you with a very bad pivot, and you're going to see why you can't just choose a value in the middle.
Yeah, it's not quite what I meant, actually.
Oh,
Yeah, so what I was asking is, so we should pick the 5 as the pivot, and then in the end, we had to shift 5 into the middle, into down. But if we have the pivot at the middle, at the very beginning,
like
in the middle of the array,
uh-huh.
then we don't have to shift it into the middle at the end.
Finding them,
Like not the actual middle value, just the middle index.
I know, but I'm just trying to think through this and make sure I get this correct, because I feel like you wouldn't properly, it would make the programming of going up and down a lot more difficult. It would introduce more potential for mistakes on the one, and I think with the if statements, the if statements would override what you'd be getting with the swaps, the additional if checks, to make sure that you're not accidentally swapping the pivot.
Okay.
So I think that, so anyway, we swapped this now, and so now 5 is in the middle, so now we've got everything less than the pivot, and everything greater than the pivot, so now we can recurse. So this is called, this thing where we take it and we separate it into the things less than the pivot and things greater from the pivot is called the partition function. And that's basically the main work of Quicksort. Quicksort basically is the way the Quicksort algorithm looks is something like this: sort, array, start, end, where these are the starting and ending indices. And then what you do is that you basically do this. You say pivot index is equal to partition. The array from the start to end, so you can get that subsection in, right? And it gives you and it does all that manipulation, and it gives you the index of the pivot, which is important because you do have to know where it is. And then you just simply say sort array. Oh, and basically you do this if the array size is greater than a certain amount. There's conditions here that we'd put in, but because you do have to have an ending condition, right? But sort array start to pivot index -1, right? So everything up to, but not including the pivot. And then you want to sort the array from everything after the pivot. The end. And so now we're able to sort this, and it ends up being a pretty good good way to sort things. Now, worst case scenario is O of n. And again, you can find this algorithm like everywhere, so don't worry if you didn't copy it down. Here's an example of where Quicksort, as I did it, is terrible. Okay. Let's go ahead and just do it, make it only slightly bad. 2, 3, 4, 5, 6, 7, 8, 9. All right, so 2 is going to be a pivot. We're going to look up for the first item that's bigger than it. Up. And then we're going to look down for the first item that's smaller than it. Down. Swap them. And 3. look up for the first item bigger than this, down for the first item smaller than this, which is here, and we're done. And it seems like great. We've just, we finished pretty quickly. We didn't have to do many swaps, but now we go ahead and swap our, we now do the second thing where we swap the pivot and down. Cool. Swap pivot and down. Okay. And now we've successfully divided this into everything greater than our pivot and everything less than our pivot. And we didn't really do much, right? It's unbalanced, just like an unbalanced tree, which means that we're essentially, again, kind of falling into that whole linked list with extra steps territory. And so if we're unlucky, we basically keep just chopping one off. So part of the partition, what we do in the partition function is that you can stack the deck. Like what we do is that maybe instead of, so what we can do instead is maybe like we choose like the first item, the middle item, and then the end item, and choose the median of those. But then we'll see that basically that in this case, that still doesn't do too well because that gives us 7, which gives us a better result than 2, but still. Finding the median in this case, right, if we're looking through all the items, takes O(n) time. So don't necessarily want to add an O(n) operation to here if we don't have to, right? We want to keep it optimized. Now, what does Java do for sorting? That's a very good question. What do programming languages actually use for sorting? When we're going to do this by going into arrays, let's go to collections, Java, right? Let's actually go and look at what these things do. Collections, Java, let's go 11 because 11 is a long-term release. Okay, so Control F, sort, because, right, there's a sorted algorithm. Oh, notice it said, so documentation for polymorphic algorithms include implementation rows higher than parts of this. Implementer should be free to substitute other algorithms. For example, the algorithm used by sort does not have to be a merge sort, but it does have to be stable. Ooh, interesting. Stable, right? So let's look at sort. So here we bring in a list. Okay, and then let's go to, is there other, and then arrays, and then arrays sort Java 11. This is the other place I want to look because actually this is really important. It's like, why are we learning all these sorting algorithms? Why in the world? Because they also have features. So that's sort. Notice that it has two, it will have two, we have multiple specifications here. Sort. Boo. This is less than useful because sorry. Parallel sort. Let's see, sorts. That's interesting. Sort. Sort's an array. You can just grab array of integers. And then sort object. All right, collections. So sorts, so first off, sort over here takes in, the sort is guaranteed to be stable. Equal elements will not be reordered as the result of this sort. In other words, if we're sorting cards and the 5 of diamonds comes before the 5 of hearts, then our output, the 5 of diamonds will come before the 5 of hearts. We're guaranteed that those two things aren't going to swap with each other because that might be important. Let's see, it doesn't have the implementation detail here, but this should. Yes, sorting, for sorting integers. If we are sorting integers, then it says we use the dual pivot quicksort by Vladimir Yaroslavsky, John Bentley, and Joshua Bloch. It offers log n performance on many data sets that cause other quicksorts to degrade to quadratic performance. So in other words, right, we use a trick with 2 pivots which I don't go into because that sounds really hard. And by using the two pivots there, they are able to avoid going to n squared. Okay, that's interesting. Now we don't care about the whole. Now here, what's interesting to note is that we don't have the stable thing because integers are integers. It doesn't matter whether 5 is 5, right? But with objects, that might matter, right? With objects that are like that represent cars, this might matter. So we use Quicksort for basically any kind of primitive. On the other hand, sort object, which has 7 matches, so much easier to go to. This sorting algorithm, it's guaranteed to be stable. It's stable, adaptive, iterative. So, let's not. So anyway, it requires far fewer than n log n comparisons when the array is partially sorted while offering the performance of traditional merge sorts. Typically, so in other words, what they're referring to is that they're using Tim sort over here, which is the sort that was created for Python, and people thought it was great, and so they used it for in all the other programming languages, and now it's kind of the standard for sorting objects, because again, we don't know if with primitives, we don't care if you've got 5 5s. We don't care which 5 goes before which one. They're just 5s. But with objects, we don't, with equal values, the user might care. So that's the whole thing about algorithms being stable. Basically, that they don't swap those 5s around. Now, Tim sort is essentially a kind of variation of the sorting of merge sort that implements insertion sort as well. And what that does is that they observe that most data that you gather, and if you're trying to sort it, occurs in what are called runs, which means that the data is basically going to go up, and then it's going to go down, and then it's going to go up. And maybe you have a couple of weird outliers in there, but like if you're trying to sort a bunch of temperatures or stuff, temperatures go up and then they go down. There's no gaps between them, right? If you're doing observations of something of a stellar object, it's going to come towards you, and then it's going to go away, maybe come towards you and away again, and then, but not get, but there might be local minima and maxima. In other words, local high points and local low points that aren't necessarily the highest highs and the lowest lows. But those runs, if you can take advantage of those runs are easy to sort. This is also part of the reason why I emphasize insertion sort as part of your learning process. Insertion sort is fantastic. It's one of my favorite algorithms. Also, again, this is kind of what convinced me that Wikipedia is awesome for computer science, because look, it's got animations. You don't get that in your textbook. You really should. And I mean, in the textbook I'm writing, I'm just going to simply steal these things or link to them because, Creative Commons. It's insertion sort's crazy interesting because for small data sets, it's very efficient. It's adaptive, which means that basically if it's already mostly sorted, if there's like only one item out of place, it only takes one O of n time to sort the entire thing. O of n, by the way, is the amount of time it takes to check if something is sorted. So this checks if it's sorted while it's doing that. If the thing is already sorted, awesome. It's in place, and then this last one is actually really interesting. Online. It's an online sorting algorithm. That doesn't mean it's connected to the internet. That means that basically that if you are busy, it means that basically if you've only got half your data and you're waiting on the other half of the data, you don't have to wait for that other half of the data to start sorting it. You can just start sorting on what you have. If you get more data later, you can combine that with your already sorted answer, and it's not going to affect the runtime, the overall runtime. So online algorithms are pretty good. Other algorithms, they just would have to throw up their hands and start over. Okay. Typically when you manually sort things, you typically use insertion sort. So insertion sort's great, even though it's O of n time average and worst case, but it is pretty cool. Basically, the way insertion sort works is that basically you start creating a sorted section, and then basically you take each item from the unsorted section and put it into your sorted section in the appropriate place. So here, right, 3, we're trying to sort next. 3 comes before everything else, so we're going to put it before 3, up before 5 and 6. 1 is our smallest, now we're going to take 1. 1 is the smallest item of all, it's compared to all the other things we have. So we're going to basically compare it to each thing, make sure it's smaller, and then end up putting it at the front. 8 is bigger than 6, so keep it there. 7 is smaller than 8, so move 8 over. 7 is bigger than 6, so we know it fits between those. So 2 is smaller than 8. 2 is smaller than 7. 2 is smaller than 6. 2 is smaller than 5. 2 is smaller than 3. And at that point, we can stop because and put it into the right place. Essentially, it's a kind of just very natural sorting algorithm, which is cool, just because it's natural. And that's a cool coincidence. Just because it's looks natural and natural for humans to perform doesn't necessarily mean it's a smart way to do things. But in this case, it does. It's a fairly good sorting algorithm to know about. Yeah. All right. And so I've lectured for about half an hour. So I will, on Thursday, will cover another sorting algorithm called Radic Sort, which is different than all the other sorting algorithms because it doesn't use any comparisons. It doesn't work by comparing any two numbers. No two numbers are compared to see which one is bigger and which one's smaller somehow. It's magic. It's not magic. It's just queues. Queues are actually very powerful data structures. You'd be surprised. All right. Okay. Just remember, like, this is an exercise in data gathering, so I want you to try to gather plenty of data for this one. So, create good sized arrays, do multiple runs and average them together, and then put that on a graph. It's the hardest part about this, or the most annoying part of this, is data collection. Yes.
Should we compare linked lists and arrays?
No, we can just do arrays.
Okay.
Make it simple arrays. Linked lists are useful